Welcome back to our video series on VASA. Part 2 is all about pathfinding. We'll go through 3 examples. You'll learn the parameters of VASA's pathfinding nodes. But first, let's make sure we understand how to control the size of the voxels in VASA. Okay, so to understand the voxel sizes, what we'll do is we'll look at a single voxel. So here I've got a empty Dynamo workspace, and I'm going to start by creating a single point. So I'm going to right-click, type point, enter will get me the point by coordinates node, and then I'm going to double-click and type in 0.01 and set that as the X, Y, and Z coordinates. The reason why we're doing that is just to move the point slightly off the origin, because if it turns out, if we zoom in, if the point is right at the origin, it's actually on the boundary between several voxels. So here we've offset it slightly from the origin to make sure it's entirely within one voxel. Okay, so now now we're going to voxelize that one point to get one voxel. So in the VASA menu, we'll go core, voxel model by geometry, and let's just create a display voxels node because we'll need that too in a minute. And we'll connect the point to the voxel model by geometry node. To voxelize it, we'll also give it a coarse voxel width. We'll just use 1, and let's assume we're in meters for this example. So 1 meter for the coarse voxel width and display. So here we have one voxel. Just going to take a closer look at it. Okay, so how large is that voxel? Well, it turns out it has a width of 6.25 centimeters and a height of 25 centimeters. So 6.25 centimeters X and Y, and 25 centimeters in the Z direction. You might be asking, where do those numbers come from? Because in the example, in the graph, all we did is supply 1 meter as a coarse voxel width. So how did we get 6.25 centimeters and 25 centimeters? Well, that's where these LOD parameters come into play, a vertical LOD and finest LOD. LOD stands for level of detail. And what that is it's an integer that tells you the number of times you divide the coarse voxel width in half. So the vertical LOD is a level of detail in the vertical direction, and we're not actually giving it a parameter here, but it's using the default. The default is 2. So that means in the vertical direction, the coarse voxel width is being divided in half twice. So 1 meter divided in half, that's 50 centimeters. Divided in half again is 25 centimeters. So that's why the height is 25 centimeters. And so that's in the vertical direction. So if you have an LOD parameter that doesn't say vertical, so finest LOD or voxel LOD, that's always in the horizontal direction. So in the horizontal direction, we're also using the default value, which you can see is 4 there. And so we're taking the voxel width and dividing in half 4 times. So 1 meter, divided in half twice is 25 centimeters. Divided in half a third time is 12.5 centimeters. Divided in half again, a fourth time is 6.25 centimeters. So that's where those dimensions are coming from. And we can change them. So what we'll do is move things around a bit and create an integer slider. Click integer slider. Let's set the min and max. The min should be 0. The max for levels of detail is 5. 5 is the finest we can go, the finest level of detail. So let's set that to 0. And now let's connect that just temporarily to both the level of detail parameters, vertical and horizontal, and take a look at this. So this is the coarsest possible voxel. It's 1 meter cubed. because the level of detail is 0, so it's being divided in half 0 times. So now if we increase that to 1, it's divided in half in all 3 dimensions. Now it's 50 centimeters cubed, 25 centimeters, 12.5 centimeters, 6.25, 3.125 centimeters. And that's as fine as we can go without changing the coarse voxel width. So, if we try to go to level detail 6, we just get an error. I'm going to undo that. Okay, so that's one way to change it. But normally, the intent of VASA is that you may have a different size of voxel in the vertical direction. So we're actually going to undo the connection to the vertical LOD. And now if we change the slider, we're only controlling the width of the voxels, not the height, which is more this is more how VASA is intended to be used. Let's leave this at 4, the default. The idea is, the reason why it's called finest level of detail is the idea is you'll voxelize once at the finest level of detail that you want, and then if you like, you can perform operations at coarser levels of detail or lower integers. So, for example, let's just I'm just going to right click. Let's pretend we're doing a visibility from direction analysis. Let's type in path model and pretend we're doing some path finding. Of course, it doesn't really make sense to do any of these operations when you just have one voxel, but just to show you what this could look like. So, you see all of these nodes have a voxel level of detail parameter, which defaults to -1. That just means by default, it will use the finest level of detail. So everything is being done at level of detail 4 or 6.25 centimeters in the horizontal directions. But what we could do is if I copy that slider, we could say, oh, maybe we want to do visibility at a coarser resolution. Maybe we want level of detail 2, so 25 centimeters in all 3 directions. Or maybe we want to do pathfinding at level detail 3, which is 12.5 centimeters, 12.5 centimeters horizontally, 25 centimeters vertically. So this is the kind of thing we can do if we want to get into the advanced capabilities of VASA, is to have different analyses at different resolutions in X and Y, but the same resolution in the vertical direction. Okay, so now we know a bit more about how voxel sizes work. Now let's check out the pathfinding examples that come with VASA. So let's go to File, Open. I won't bother saving. And here we have the examples that come with VASA. We did the overview example in the previous video. In this video, we'll be doing the 3 next examples. So we'll start with 02 VASA pathfinding in 3D. And we'll open that. Okay, so it's loaded up. You'll want to read the description comments, but I'm just gonna skip over that now. And so just to give you a quick overview of what we're seeing here. Again, we have triangle data coming in as from STL files. You could use data from Revit though, of course. That's getting voxelized. We're voxelizing both building triangles and the glazing, because glazing is a travel barrier, so we need to voxelize it to do pathfinding. We create a pathfinding voxel model using the union operation to combine the two other voxel models, and then we're displaying that. And you can see we're using this slightly translucent color to display it. Click advanced, it's sort of half translucent. you may or may not like that. It lets us sort of see through the model a little bit and see the path a little bit better. It does let you see these squares, those are not voxels. These large squares here are 16 by 16 voxels. If you want to see what an individual voxel looks like, we can zoom in on this column, and it's fairly clear. It's quite, remember, it's 6.25 centimeters using the defaults, so it's quite narrow. And we're also seeing this path. So if we go back to the graph, we can see the voxel model for pathfinding is going into this path model node. And just to show you where that is, it's under VASA pathfinding, path model by voxel model. So you always have to create this path model node, and then you can create a path using the path model and supplying 2 points. So the 2 points are this one down here and this one up on the 3rd floor. Sometimes the display gets a little weird when you select the points. And then we're displaying the path. We're actually converting the path into a curve, and then this is just a regular Dynamo curve, and then we're just displaying the curve in yellow using the regular Dynamo geometry color node. And there's some other features we can use as well. Like if we have a path, we can use this path length node. So if we go to VASA on the left, pathfinding path, there's the path length node. There's the node that creates the path from a path model. So we can use that to figure out the length of the path. Let's now go through this. Well, actually, let's quickly just change the locations of the endpoints. So there's 2 points. One point is called the source, and that's the point down there. The other one's called the sample point. The reason why they're called source and sample is the source is the source of a distance field. We don't see the distance field, but it's how the path's being calculated. So it creates a distance field from the source point, and then the sample point is a point that's being sampled on the distance field. It does not mean that it's the start and the end. Like the source is not necessarily the start. When you after you create the path, you can create a curve from the source point to the sample point if you want. But if you look on the left, you can also create a curve from the sample point to the source point. So the source and sample determines how it calculates the path, but the direction of the path is determined later based on which of these nodes you use to actually get access to the path. Okay. So let's go and now change the sample point, that point at the top right there. So if we move that, let's move the y coordinate up, and now we can see it's actually rerouted through a different door. I'm going to undo that so you can see it going through a different door there. Now let's go and try moving that point down to the other side of the building. So I'm actually gonna, it's 23 meters. I'm gonna change it to negative 23 meters. Let's see where that puts it. That puts it way down at this end of the building. And now you can actually see it's chosen a different staircase to go up. It's going up this staircase over here. And if I undo that change, you can see it goes up this staircase. Okay, now let's learn a little bit more about how this works. So we have this path model node. What does it do? Well, the path model node, what it does is it determines what voxels are considered traversable, what voxels are considered places that a person might walk. So we can actually take a look at those traversable voxels if we go to path model under VASA pathfinding. and click traversable voxels. And now just apply the path model to the traversable voxels node. And that gets us a voxel model that shows us what the path model actually looks like. And now we can display that. So I'm going to right click, type display voxels. And let's give it, okay. I'm going to do a couple things here. I'm going to give it a different color so I can tell which voxels are the traversable ones. So let me right click, type PAL for palette. I'll select this color here. Okay, so those are the traversable voxels. It thinks it doesn't actually know what elements are which, so it thinks you can walk on the roof. That's because the roof is shaped in a way that would allow a person to walk there. So it doesn't realize that it's the roof. So the roof is traversable. And so now what we'll do is let's just insert a crop node. We've got a crop node up here. I'm actually going to click this and click the slider, shift click, and I'm going to copy those nodes just to save some time. And I'm going to connect the traversable voxels to the crop node. And so now we're cropping off the top of the traversable voxels. I'll just move these around a little bit. Okay, so now we can take a good look at what voxels are considered traversable. And I'm actually going to do one thing first, and that's I want to move this path up, because now the path right now is sort of inside the traversable voxels, so sometimes it's going to disappear on us. So I'm just going to move that up slightly. So let's just drag the display path node out to the right. Let's right click, type translate, and we're just going to translate that path up in the Z direction by, let's just do it by or millimeters. 250 millimeters, that's 25 centimeters up in the Z direction. Let's hide that. Okay, now we're seeing the path on top of the traversable voxels. Okay, now let's have a look at this in more detail. So these are the voxels it thinks are traversable. You can see it covers the floor as well as the stairs. So the way it works is VASA thinks that any surface is it can walk on any voxel that's at the same level as the current voxel, or that's one voxel up and one voxel down. So with the stairs, it can go one voxel up, so one step up at a time, or one voxel down. If it goes up by two or more voxels, it thinks it's a barrier, like a wall. Or if it goes down by more than two voxels, it thinks it's a drop off, so it won't go there. So this column, for example, and all the walls, these are barriers. And there's actually a bit of a buffer zone around these barriers. So it won't actually go right up to a column or right up to a wall. It also won't go right up to the edge of a drop off. And the real model actually has railings, but I've excluded the railings, but it still won't go off the edge. Okay, so those are the traversable voxels, and as long as the whole area is traversable all the way from your source point to your sample point, it should be able to find that path. Some issues can occur if you move a point so it's right. Well, obviously, if it's in a barrier, then it won't find the path. Also, if your point is not in a barrier, but so close to it that it's in this zone where there's no traversable voxel underneath. The point actually has to be directly above a traversable voxel or one voxel below. those are the rules. So it's if you're one voxel underneath these orange voxels or above it somewhere, then it will find the starting point in the traversable region. So that's a common mistake would be to put a point either off the edge of the model or in a wall or too close to a wall, and then it will fail to find a path. Maybe you will actually give that. Should we quickly try to find a point that doesn't work? If we go to the source point, type in 8 meters instead of 12 meters. Yeah, and here we've found a point where it's not above the traversable voxel and it's not finding the path. By the way, when it doesn't find the path, what happens is you'll still get a path object, but then all the subsequent operations will fail. Like you won't be able to create a curve. And if we go to path length, sorry, what I wanted to do was to go to is to use the invalid node. So if I connect this to path is valid is false. So if is valid is false, the path is not valid. If we go and change the x coordinate back to what it was before, then it will find the path again, and then is valid is true. Okay, so that's how valid and invalid paths work. Now let's just go over 2 parameters to the path model that we didn't go over before. So one is the agent diameter offset, and one's the agent height offset. So these are the approximate sizes of the agent that would be traveling in voxels. So if you could imagine a human was the object that was going to travel along the path, then how wide what would the diameter and height of the person be in voxels approximately? So for the diameter, the default value is 7. Here we're giving it a value. We're giving the value 7. So what that means is 7 voxels is the approximate width of a person. That determines how what size doors they can go through, for example. And if we type in calculator and bring the calculator up, we can just see that 7 voxels times 6.25 centimeters, so 43.75 centimeters. Again, it's very approximate. We shouldn't be too exact when we choose these values. We should choose a value that gets the paths through to the places that we want to go, but doesn't allow us to squeeze through very small gaps that no person would be able to traverse. So so that's how that parameter works. And the agent height is very similar. It's 4. So we can get through these openings of at least 4 voxels in height, which is each voxel is 25 centimeters in height, so about 1 meter. That might seem a little bit low, like shouldn't be able to get through a 2 meter gap. Well, remember that when you voxelize geometry, you distort it a little bit. Like you can actually, if you have a door that's 2 meters tall, just for example, the bottom of the door when you voxelize it could come up by about as much as a voxel, which is 25 centimeters, and then the top could come down by 25 centimeters as well. So that 2 meter opening could become a 1.5 meter opening. So to be safe, we choose a height that's quite low by default, 1 meter. If you make it too small, then you'll be able to walk under tables. But if you make it too big, you may not get through doorways. So that's how that's being selected. You can change it if you want, but just check to make sure that your paths are still going where you want them to. So finally, what we'll do is we're going to change now. we're going to change that level of detail that we're using for the entire calculation. So if we go back to original voxel models, you see that the finest level of detail, both of them are being connected to this slider here. And we're using the default value, which is 4. But let's actually slide that down to 3. And now we have 12.5 centimeter voxels. So the reason you would want to do this is because now you have quite a bit fewer voxels. You actually have 4 times fewer voxels when you cut the horizontal resolution in half like this. So you can get your results much faster, but you have to be careful to make sure that the paths are still getting through. So now if we take a closer look, we can see that there's a much bigger gap first between the traversable voxels and all the walls, and we're actually getting gaps on the stairs because the sort of the agent width determines how steep a slope you can go up or down. So now we have the same agent diameter offset as before, 7, but now our voxels are twice as big. So now the diameter has doubled. So what we actually want to do now is we want to take this agent diameter and decrease it. So instead of 7, let's decrease it by 1 step first. If we decrease it to 6, okay, that's already restoring the path. So now it's working. But I would actually recommend decreasing it all the way to 3 if we want to use 12.5 centimeter voxels. So yeah, you have the flexibility to change resolution, but you have to be careful to change their parameters as well. One last point is about the vertical level of detail. Remember, right now that's not being set. We're leaving it at 2, so 25 centimeters. So that tends to work because 25 centimeters is taller than a typical step, and so that means that when you go up a step, you're only going up 1 voxel, and so VASA can do that. If we were to let's say we were to change the vertical level of detail from 2 to something finer, let's put a 3 there, which will change it to 12.25 centimeters, which is smaller than a step. Now you'll see that certain steps are actually 2 voxels tall. Some of them are still 1 voxel tall. Some are 2 voxel talls. So now VASA thinks there's barriers on that staircase. So that's why the defaults are the way they are. With we recommending 1 voxel, a 1 meter coarse voxel width, and a vertical level detail of 2. That ensures that you can get up and down these stairs. It also works to have a coarse voxel width of 4 feet. Then your voxels by default will be 1 foot high, 4 feet divided in half twice, and that will also get you up and down the stairs. Okay, I think we've covered this example enough. So let's move on to the next example. And that's pathfinding in 2D. So we'll load that up. So here's our pathfinding in 2D example. We'll take a quick look at the graph. And we can see our 2-dimensional layout. Pathfinding in 2D is something we can actually, there's a variety of packages that could be used for 2-dimensional pathfinding. One of them is the space analysis package. I have it installed here on the left. That was actually the space analysis tool we developed before VASA. It's kind of a predecessor to VASA, and it only works in 2 dimensions. So you could use that, but here we're using VASA because you may want to use the same tool for 2D and 3D. So here we have a 2D pathfinding model example in VASA. So the way this model works is we're starting with line data, a bunch of lines. So that's coming in from a SAT file that's included with the package. And if I let me hide everything here. I'm going to select all these blue nodes and right click and hide them all, just so that we can take a look at the lines that's being used as the input data. So here we have a bunch of lines, and that's what's being voxelized. For this data set, we're actually in meters, not millimeters. So the coarse voxel width is 1. And if I undo those changes, with the model in meters, I find it's easier to actually just, you're able to just drag these points around and see the path update. You can see if you move the point over there, it wants to go outside the building. I'm going to undo that. And so what's happening is that those lines are being fed into the voxel model by geometry node, and it's really the same as the previous examples, except for one key thing, and that is because all the data coming in shares the same exact Z value. Everything's in a plane. Because of that, VASA is guaranteed to give you a voxel model that's exactly 1 voxel high, and that's important if you're doing pathfinding specifically in 2D. So here we actually have some nodes at the top, and these aren't really needed. In fact, I could just delete them and the example still works. But what those are doing, if I undo that, all that's doing is checking to verify that the height of the model is 1 voxel. So I have this 1 voxel high voxel model. If we zoom in, we can kind of see that it's only 1 voxel high. And we're passing into a path model. And here we're actually setting the agent height offset. Instead of using default, which is 4 or 2 meters, we are giving it a height of 1 voxel. And that's what we do to indicate that we want to do a 2D pathfinding analysis in VASA. And when you do that, that will actually fail if your model is more than 1 voxel high, but ours is just 1 voxel. And then when you do it, and now we don't have to worry about having a ground underneath the path. It's just the voxels are just obstacles, and everything else is a traversable area. So if we follow this through, we've got the path model being created the same as before. We're looking at here we can see the traversable voxels if we want, and we're actually displaying the non-traversable voxels. So what we're doing is here are the traversable voxels. I'm gonna plug that into the display node. So these are all the areas you can traverse, but we're using one of our favorite tricks. If I just undo that change, we're using the invert followed by the subtract node to turn the traversable voxels into the non-traversable voxels. So that's what we're seeing there. And if we go over here and change this agent diameter, we can see those non-traversable areas sort of get larger as we increase the diameter of the agent. Remember, increasing diameter of the agent means they require a larger opening to get through. So if you make that too big, then you won't be able to get through that doorway and the path will disappear. Let's undo that. Well, one last thing I'll mention is there's different ways to view a path. So here we're creating a path from the 2 points, and in the previous example, we used the path dot curve from source to sample or sample to source. So if we go to VASA pathfinding on the left, path, here we can create curves in a direction or points. So here we're using points, and so now our path is just a list of points in order from in this case from the sample point to the source point. Okay, so that's pathfinding in 2D. Now let's open up the third example, the last one we'll do today. And that's 04 VASA distance field. Okay, so now in this example, we can see the distance field in purple there. And there's two things that distance fields do. First of all, they just let us see and have representation of all the areas you can reach within a certain distance of a point. So we're using this point here, and the purple is all the areas that a person could reach within a distance of 73. This example is in feet, so 73 feet from that point. You can see the coarse voxel width here is 4 feet instead of the usual 1 meter. So that's all. So the distance field showing us all the areas that we can reach within a certain distance, but it also provides another way to calculate paths. Now, the reason why you might want to use a distance field to calculate paths is because you might have a whole bunch of paths that share a common point. And so what you want to do is you create a distance field with a certain source point, and you use that source point for multiple paths. That turns out to be more efficient than calculating each path separately when they all share a common point. So if we actually move that slider, let's start it off at 0, and as we increase it, we'll see that every time the distance field expands and encompasses a sample point, one of the other points, it will compute the path. So there's one path being computed at this point at the top right. And as we increase it, more paths start being computed. And then finally, there's a path at the bottom left. There's a sample point at the bottom left. And so we get our final path there as we make our distance field wide enough. Okay, let's see how that's working now. So we create our voxel model as usual. Then we create a path model. We always create a path model if we want to do pathfinding. Then we create a distance field. And the distance field, we give it a source point and a maximum distance. So that was that point there. And then we create that. Then once we have distance field, we use that to sample a bunch of paths. So here we create a path object from the distance field and a sample point. So here before we were using path by path model endpoints. Now we're using by distance field and sample point. And here we have a bunch of different sample points, and they're all going into a list. And then we're feeding this list into this path by distance field node, and that creates a set of paths, one for each of the sample points. And then we can see, which paths are valid. Right now, they're all valid. But if we decrease the distance and go back, we'll find that some of them are invalid. Right now, one of them, the last one's not valid. If we decrease a little bit more, now none of them are valid. I want to put that sort of halfway in between. Now 2 of them are valid. So what we're doing is we're filtering the list, so we only retain the paths that are valid, and then these get sent to a node that helps us view the paths. Remember, we can view a path. There's actually 3 ways to view paths. We can view it by creating a curve, as we saw in the first example. we can view it by creating points, as we saw in the next example. And in this example, we're using path voxels. We're actually creating a voxel model for each path. So these, if we zoom in, these yellow paths, each one is actually a voxel model, and the voxels are showing us the path. So there's lots of different options for how to show paths. And because these are voxel models, we can process them like we would other voxel models. Here we're resizing it so that it crops at a certain elevation if we want, and then we're displaying the path voxels. Okay, so that's this distance field example. You know, one thing I just wanted just to show you, because you know, there's lots of things to think about when you're doing these analyses, and one of them is how furniture works. I mean, you don't need to include furniture, but if you want to include furniture, you have to remember that the furniture has to be 2 voxels high if it's going to be a barrier. So actually, in this example, it turns out that the furniture by default, some of it's only 1 voxel high. So if I set this to 0, we're just going to see the original data, and the bed is the bed and the couch are actually only 1 voxel high, so it's actually possible. Well, I'm having trouble dragging the point, but it would actually be possible to walk right over the bed or right onto the couch. So if we don't want that, we've put this offset in. If we set that to 1, what that's doing is it's that 1 is going into a expand along Z operation. So this is taking the furniture voxels. So here's the furniture triangles that are being voxelized. It's taking the furniture voxels and expanding it by 1 voxel in the upper Z direction. So if we go to our VASA menu again, under operations, surface operations, there's various operations you can use to expand or reduce voxel models by a small amount. So here we have expand along Z. So when we when we set that offset, it moves it adds a voxel on top of all the furniture, and then the furniture gets treated as a travel barrier. Okay. So I think that's good for this video. Again, you may want to go through these examples on your own to make sure you understand all the parameters and calculations, and then please check out the next videos in the series. So go and find the video description, and you'll find links to the other videos. Thanks for watching.